Next up, we have Branzdon. I think Branzdon's our youngest speaker. Really excited about his talk. Not going to give away all the details, but some really neat exploitation stuff he did on iOS and macOS. So let's give a round of applause to Branzdon and welcome him to the first Objective by the Sea conference.
All right. Thank you. Yeah, super excited to be here. Thank you for sticking around to the very end. Well, I guess Patrick's still talking after me, so. So sorry about that. Hey, everyone. My name is Branzdon, and I'm going to be talking about how you can elevate privileges on macOS by crashing maliciously. Really, this work was originally based on an exploit that I did on iOS, so I'm kind of going to be mixing the two a little bit. Sorry about that. I know it's a macOS conference, but... Okay, so first a little bit about me. I was, until very recently, an independent security researcher, but about 3 weeks ago I actually joined Project Zero, which is Google's applied cybersecurity research team. So it's kind of a bit weird since this talk is research that I did before joining Project Zero. So just to be clear, this is all like independent stuff. My opinions here do not represent Google. So yeah. I guess I focus a lot of my security research on macOS and iOS. I graduated from Stanford in 2016 and 2017. I was among those who discovered the original variant of the Pegasus spyware's kernel code execution vulnerability. There were like so many people who did that. And I also developed some open source tools, including memcontrol, which is a kernel inspection tool on device, and an IDA Pro toolkit for analyzing Apple kernel cache files called IDA kernel cache. So what's the context for this research project? Why did I begin looking at crashing? Well, really, it all began when I started looking at a crash log on the device, and I realized there's a heck of a lot of information in these crash logs. So you can see there's some general information about like what is going on. We have a backtrace, which is usually symbolicated about what the actual crashing thread stack looked like. We have the register state, so the values of all the registers, and even a listing of all the binaries that have been loaded into your process address space. And this log is actually generated on the device. So there's a lot of processing that's going on to generate this crash log. And that really got me thinking, you know, if there's a lot of processing going on here, I wonder if that makes a viable attack surface. So can you like take advantage of this processing to elevate privileges or something? More formally, what is this research project? We're going to be focusing on crash reporting on macOS and iOS. And specifically, we're going to be targeting macOS 10.13.5 and iOS 11.2.6. And our goal is going to actually be pretty simple. First, we're going to try to find a zero-day vulnerability by looking at the crash reporting machinery. And then we're going to try to elevate privileges on macOS. And after that, we're just going to elevate privileges on iOS. So just see how far we can go with whatever bugs that we find. And once again, why did I kind of start looking in this research area to begin with? Well, because it seemed like kind of an absurd place to look for bugs. Like, I don't know about you, but I've never seen an exploit that works by just like crashing your own process maliciously. It seems kind of like a dumb way to attack a system. So I figured that Apple probably hasn't given crash reporting the security auditing it really deserved. Okay, so before we can actually go into the bug, let's talk a little bit about inter-process communication, which is really fundamental to understanding what's going on here. So IPC on macOS and iOS is based on Mach ports. Mach ports are reference-counted message queues that are maintained by the kernel. Arbitrarily, many processes can send messages to these queues, but only one process at a time can receive messages out of the queue. And in user space, a Mach port is referenced by a Mach port name, which is just a fancy name for an integer, which is like a file descriptor. So in the same way that a file descriptor in user space is a number, which represents a file, a Mach port name is just an integer, which represents an in-kernel Mach port queue. Now, there's also some terminology related to Mach ports. The ability to send messages to a Mach port is called a send write, while the ability to receive messages out of a Mach port is called a receive write. All right, so now let's talk about these messages. A Mach message is structured data that gets sent to a Mach port. It's queued in the kernel until the owner of the Mach port actually listens for the message. And a Mach message can actually contain arbitrary data as well as send and receive rights to Mach ports. What this means is that you can actually send a send right to a Mach port to another process by embedding the send right in a Mach message that gets delivered to that other process. So basically, these send and receive rights can be transmitted around to other processes over the very IPC mechanism which they're defining, which is pretty cool. Okay, so now let's talk about some special varieties of Mach ports called task and thread ports. Now, these are special Mach ports, which means that the receive right is actually owned by the kernel. So any messages that you send to these Mach ports don't get received by other processes. They're just processed by the kernel itself. Now, a task port is a special port that can be used to control the corresponding task object. And a task is basically just the Mach name for a process. So if you have a task port, you can call functions like Mach VM allocate, which will cause the kernel to allocate virtual memory inside that process's address space, which is a very powerful kind of like remote control mechanism for a process. And similarly, thread ports allow you to control an individual thread. So for example, if you call thread set state, that can be used to set the values of the registers in a particular thread. All right, so we actually just talked about task and thread ports, and I would be amiss if I didn't mention that there was a rich and long history of abuse of task ports in exploits on both macOS and iOS. And that's because there's a formula for how to go from holding a task port to actually taking control of a process. So if you have a task port, you can call Mach VM read and Mach VM write to directly read and write the process's memory. And that's basically it. I know, Apple's really made our lives difficult with this. They've like blocked all the APIs and like gated everything. It's really difficult. Actually, it's a very important thing to keep in mind. If you have a task port for a process, you own that process. You can directly control it. So let's get back to the background info. Now that we've talked about Mach ports, which provide inter-process communication, let's see what daemons on macOS and iOS look like. macOS daemons are called Mach services, which means that you communicate with them by sending and receiving Mach messages. Each Mach service is identified by a name. So for example, com.apple.core-services-d is the name for the core services daemon. And how does a client process actually gain the ability to talk with a service? Well, the launchd process, which we've been talking about in some other presentations, actually vends all the Mach services on the system. So as Mikkel mentioned earlier, it basically serves like a DNS server for all of your Mach services. You give it a name, and launchd will actually send you a message back with the service's Mach port. So a client is going to just send a message to launchd saying, hey, I want to talk with a service. And launchd will send a message back, giving you a send right to the service's Mach port. All right, so that's basically all the background information that we're going to need. So as a reminder, the focus of this talk is on crash reporting on macOS, and our goal is to find a zero-day vulnerability, elevate privileges on macOS, and then elevate privileges on iOS. All right, so now let's take a look at crash handling. What is actually going on when a process crashes? Well, crash handling is based on Mach exceptions, which are a generalization of your traditional BSD signals. So just like there are many different types of signals, such as SIGINT and SIG-SEGV, there are also many different exception conditions. So for example, X-bad access is an exception that occurs on an invalid memory access, while X-crash is an exception that occurs when a process terminates abnormally. And for each of these exception types, you can actually register in the kernel a Mach port to be notified when an exception occurs. And this notification can actually occur at 3 levels of granularity. So you can register to be notified when a particular thread generates an exception, or for when a particular thread or for when any thread in a task generates an exception, or you can register to be notified when any thread on the whole host generates an exception, which is very, very broad ability to receive exceptions. And once an exception does occur, the kernel will basically just send a Mach message containing details about the exception to the registered exception port, which allows you to process it. So how do you actually go about catching a Mach exception? Well, you need to implement an exception handling service routine, which has this prototype. So the exception message will actually contain the thread and task ports of the crashing thread, as well as other information about the exception. And when this message is received, it'll be parsed by auto-generated code, and then the contents of the message will be passed to this function as parameters. Now, the code that calls this function is auto-generated by MIG, which is a tool that generates mock message parsing code. And the details of MIG aren't that important. But what is important is that because this function is called by MIG, there are very important semantics around the return value. So if this exception handling function returns success, then that indicates to the MIG code that the exception was handled and that it'll tell the kernel to resume the crashing process. However, if this function returns failure, then the MIG code that called this function will deallocate the thread and task port sent in the message and then tell the kernel to try the next exception handler. So these semantics around the deallocation of Mach ports on returning failure are absolutely critical. All right, so what does this exception handling strategy actually look like? So here's a hypothetical example where our process, which is blanket in blue, has a registered exception port for X bad access. And that port is owned by this crash handler process in red. So when blanket accesses an invalid memory address, the kernel will check its exception table and see that there is indeed a registered exception port for X bad access. The kernel will then enqueue a mock message containing details about the exception on the port, and when the crash handler process listens on the port for new messages, it's going to receive a copy of that message in user space. And at this point, the crash handler process can use the task and thread ports in the message to inspect or even to fix up the crashing process. So, who is this crash handling process on iOS? It's a binary called ReportCrash, and this one binary is actually responsible for running two separate mock services, each in its own process. The first and most important is a service called com.apple.reportcrash.root, which, for the sake of brevity, I'm just going to call ReportCrash. Now, this service port is the host-level exception handler for Xcrash exceptions. What this means is that this port is going to receive an exception message whenever any application on the device terminates abnormally. And then the exception will be delivered to the ReportCrash port, and ReportCrash will inspect the process and generate a crash log. The other service is com.apple.reportcrash.root.self, which I'm going to call SafetyNet because that's its name on iOS. And it kind of makes more sense as a name for reasons that you'll see. So SafetyNet is the task-level exception handler for when the first service crashes. And the whole reason that SafetyNet exists is so that it avoids ReportCrash having to handle its own exception messages. So when ReportCrash crashes, it actually has a safety net so that it doesn't have to infinite loop handling its own exceptions. So what makes ReportCrash worthy of investigation? Why is this an interesting target to look for vulnerabilities in? Well, if you actually start an instance of ReportCrash, you'll see that it has root privileges, and also it's completely unsandboxed, which makes it a very appealing target, because if we can get code execution inside of ReportCrash, we now have a large amount of privilege. So let's talk about the vulnerability. I basically just opened up ReportCrash in IDA Pro and decompiled it to look at the exception handling service routine. So remember, this is the function that gets called whenever an application on the device crashes. And here's the code. So this function gets called by auto-generated MIG code, and the thread and task port parameters here are parsed directly from the exception message. ReportCrash first is going to set the return value to current failure, and then if the message was not sent by the kernel, the ports sent in the message are going to be deallocated, and then failure is returned. So now this is a problem because this function is called by MIG code with very important semantics on the return value. Remember, if the return code is failure, then the MIG code that called this function is also going to deallocate those mock ports. And this is really problematic because mock ports are reference counted, which means that we effectively have decreased the reference count on those mock ports to one less than ReportCrash expects. And this can effectively lead to a type of situation almost similar to use after free, except it's a mock port use after free rather than a memory corruption use after free. So what does this process of mock port use after free look like? This is basically an attack called mock service impersonation, where we're going to trick substitute one Mach port with another, and then do this all without ReportCrash knowing. So to start with, a ReportCrash is going to be talking with some privileged system service, which is in yellow. So ReportCrash has a send right to the privileged service. And we're going to try to use this vulnerability to trick ReportCrash into talking with us instead. So first, we're going to generate a malicious exception message where the thread and task ports in this message are not real thread and task ports, but instead are send rights to the Mach service ReportCrash is talking to. So this is a malicious exception message because this would never be generated normally. But the kernel is never going to stick, regular Mach send rights in an exception message where the thread and task ports are supposed to be. But because we can actually talk to ReportCrash ourselves, we can craft this message, we can send it to ReportCrash directly, and then ReportCrash is going to receive the message, and it's going to process it with the code that we looked at earlier. And now because the message was not sent by the kernel, this means that the vulnerability is going to be triggered, so ReportCrash is going to deallocate the thread and task ports again. And remember, this is a malicious exception message, so those ports aren't real thread and task ports. And it's going to drop the reference count of those ports to 0, and then the port is going to be deallocated. And this is going to inadvertently free ReportCrash's send right to the service. So ReportCrash thinks that this port still refers to the service it was just talking to, but we've used the vulnerability to drop the reference count to 0, and the port has been freed, all without ReportCrash realizing it. So now what we're going to try to do is we're going to try to get that port name reused with a send right to a port for which we hold the corresponding receive right. So we're going to generate a new Mach message containing a whole bunch of Mach ports that we own, and we're going to send that message over to ReportCrash. When ReportCrash receives the message, those ports are going to enter ReportCrash's IPC namespace, and we're going to hopefully have one of them reuse the name that originally referred to the service. And at this point, ReportCrash doesn't really know that the service port was changed. Any messages that ReportCrash sends that are intended for the service are instead going to be delivered to us, allowing us to man in the middle ReportCrash's connection with the service. And so for example, this could be really useful if ReportCrash tries to send its own task port in a message to the service. Because we've effectively changed that Mach port to point to us instead of the original service, that message is going to be delivered to us, which means we now get a copy of ReportCrash's task port, and because we have a task port, we can now take control over ReportCrash. So this is a very powerful attack, but exploitation really depends on being able to find a useful service to do this man-in-the-middle on. And if we look at all the Mach ports owned by ReportCrash, there really aren't any useful targets. So even though we have a Mach port replacement vulnerability, there aren't any useful ports to do a man-in-the-middle attack on. So like any good security researcher, I gave up. And that's it. Thank you very much. No, so I'm messing with you. I actually, it might have ended there. I was all prepared to give up because this was a completely useless bug. But I actually started reversing LaunchD for some completely unrelated security research. And I found something really surprising, which is that for some mysterious reason, LaunchD also implements a Mach exception handler. And guess what? It has the same bug. Now, I have some theories as to what development technique might have led to this. But the end result is basically the same, which is that we can send a malicious exception message to LaunchD, specifically of the type xcrash, and that's going to cause LaunchD to over-deallocate the thread and task ports in the message. So here's the vulnerable code, but this time from LaunchD. So like before, the thread and task port parameters are parsed from the exception message. Then at the end of the function, the thread and task ports are deallocated, and then for the specific exception type of xcrash, failure gets returned, causing those ports to be deallocated a second time. So LaunchD is a much more promising target for an exploit. And the reason for that is because LaunchD actually manages Mach ports for the whole rest of the system, which means that there are many more targets for Mach port replacement. In addition to that, our Mach port replacement attack is now exponentially more powerful, because not only do we trick LaunchD into thinking that we own the service port, But because LaunchD is effectively the Mach service DNS server on the phone, LaunchD is going to tell all the other processes that we own that service to, which means that we now can do Mach service impersonation against almost any other process, and that process doesn't need to have this vulnerability in it, because we just trick LaunchD, and LaunchD is going to tell everyone else that we own the service as well. So it's a very nice bug to have. So how are we doing in our overall journey? We found a zero-day vulnerability in LaunchD, and so that part of our goal is achieved. We can use this vulnerability to free certain Mach ports inside of LaunchD. So at this point, we know that we want to use this primitive to impersonate a system service, and after we figure out how to do that, we also need to figure out how we're going to actually use Mach service impersonation to elevate privileges. So let's look at the first step, which is to use this vulnerability to impersonate Mach services. So let's say that we're trying to impersonate some target service, so that when a new process starts up and tries to connect to the target, LaunchD will connect them with us instead. First, we're going to send LaunchD a fake crash message to free LaunchD's send write to the target. So this is actually exploiting the vulnerability. Next, we're going to generate about 500 Mach ports, and then we're going to use those ports to repeatedly register dummy services in LaunchD, effectively just like spraying Mach ports into LaunchD's IPC namespace until hopefully one of those ports reuses the port name that we freed earlier. And we can check for success by just asking LaunchD, hey, LaunchD, send us the target port name. Once LaunchD sends back one of the ports that we created earlier, we know that we've won. And at this point, any new process that starts up and asks LaunchD to connect to the target is going to instead be talking to us, allowing us to do our man-in-the-middle attack. So let's now look at how we can use Mach service impersonation to elevate privileges on macOS. So the key to using service impersonation well is in choosing the right service to impersonate. So if we're going to elevate privileges, we might as well aim as high as we possibly can, which is to get code execution in an unsandboxed root process with the task for PID allow entitlement. Task for PID allow, if you're not familiar, basically allows you to call the task for PID system call. And because a task port means you can control a process, if I can call task for PID, I can get the task port to any process on the system, so I can take control over any process on the system. So if I need any entitlement, just inject code into a process with that entitlement, and you're done. So if you have task for PID allow, you own every user space process. So this is the best that we can hope to achieve, so let's try to see if we can actually do that. The easiest approach we can actually take is the strategy initially suggested by Ian Beer of Project Zero, which he demonstrated in his Mach portal exploit, which is to find a service to which a privileged client sends its task port. Then use the vulnerability to impersonate that service, and then trigger the client to start and man in the middle its requests. Then the client is going to think that it's talking with the original service, and so the client is going to send us its task port, which then allows us to take control of the client. And then we now inherit the client's privileges. So, sounds great, but if we actually do this and look in the services that exist on macOS that we can actually impersonate, there are basically only two that look very promising. Fortunately, they're actually great candidates, and Core Services D is actually perfect for our needs. Because clients will actually send their task port to Core Services D, and there are a lot of really privileged clients. So we can just basically impersonate the service com.apple.coreservices.coreservicesd, which was actually the same service that was used in Ian Beer's original macOS exploit code, and it basically just works right out of the box. So Core Services D, again, holds the task ports of all of its clients. And we can actually see a listing of all the task ports that it holds if you use the lsmp command. So we want to find the client of Core Services D that has the most privileges. And there are actually two of them right here. I don't know if you can actually see it on the screen. But there's spindump and sysdiagnose, which I've highlighted in red. These are actually task for PID allow entitled. So all we have to do is impersonate Core Services D and start up one of these two processes, and then we'll get sysdiagnose's or spindump's task port, and then we just execute code inside a task or PID allow process. So that's basically how the exploit works. So first we use the launchd vulnerability to impersonate core services D. Then we trigger sysdiagnose to start. The reason I chose sysdiagnose is basically just because it's easier to communicate with. Sysdiagnose is going to want to talk with core services D, so we just man in the middle sysdiagnose's connection because we've now impersonated core services D. And then we get sysdiagnose's task port, and then using that task port, execute arbitrary code with unsandboxed root task for PID privileges. Graphically, it looks something like this. So we have launch D is in the center with core services D in the blue-green color on the right. We have blanket is on the bottom and left. Blanket is our attacking process. So, the arrow represents launch D having a send write to core services D. So the first thing we're going to do as the attacker is look up core services D in launch D to get a send write to core services D. And then we're going to attack launch D by sending a malicious exception message and get launch D's send write to core services D to be freed. Once we've freed the send write, we now register a bunch of dummy Mach services in launchd and get the core services D port name reused to point to us instead. So at this point, we are now man-in-the-middling core services D. So if we trigger sysdiagnose to start, sysdiagnose is going to ask launchd, hey, who is core services? And launchd is going to reply that we are core services. So now we're directly in the man-in-the-middle position with core services D. So when sysdiagnose tries to send messages to core services, we get to receive them, and we just pass them directly along to core services. And eventually, sysdiagnose is going to just send over its task port as the normal communication protocol with core services, which means that we get that message, we use the task port to take control over sysdiagnose, and now we have elevated privileges. So let's do a quick, hopefully quick demo. You never know with these things. Where did my... here we go. So I have my repository here, and I have some shells that shell scripts that wrap a binary that does this technique. So launchd port rep root shell should hopefully work. This is being tested on the machine that I'm giving this presentation on. I'm not sure if that's a great idea. Okay. So the error that we see here is basically because sysdiagnose is already running on the system. I have not, it's possible to work around this restriction, but I have not because I'm not a super huge fan of just giving completely weaponized exploits out. So basically the way to fix this for demo is just kill it. So sudo p kill 9 sysdiagnose. Cool. And then, so we freed launchd send write to core services and did the impersonation, got a sysdiagnose task port, and executed code. Now we have a root shell. Woo. So, I should probably kill that. Not a great idea to have that open. All right. So that was nice, right? It was fun. But didn't it just feel a little bit too easy to you? Like, we just basically took stock exploit code. We didn't have to do anything. Ian Beer did all the work. So why don't we try to do something like a little bit harder? And the thing that might be a little bit harder is doing this whole thing again on iOS. And the reason that iOS is a lot harder is twofold. First, there's a lot more mitigations on iOS, so there's a lot more security features that we're going to need to bypass. And second, the actual exploiting of this bug is harder because there's an additional security check that we need to bypass. So here's the same code from launchd, but this time in the iOS case. So this is very similar to the macOS version, but it's not identical. There's one additional security check. So like before, the thread and task ports are parsed from the exception message. And then there's also this check here that wasn't there before, which is some check on something called an audit token. And we're going to have to bypass this to trigger the bug. But once we do bypass it, it's the same as before. The thread and task ports are deallocated. Failure gets returned for the specific case of X crash. So how are we actually going to trigger this bug on iOS because there's this additional check here that we need to bypass? Well, we need to make sure that this if statement is not taken. And this code is basically launchd checking that the exception message was really sent by the kernel and not some user space process. And this is really problematic for us because the kernel is only going to send an exception message when a process actually crashes. We can no longer just do the thing of just like send the message directly to launchd. And if we just try to crash our own process directly, that's not going to work because the kernel is going to stick the real thread and task ports in the exception message. And what we really need is for the exception message to contain the send write that we want to free inside of launchd. That's the whole premise of sending a malicious exception message. So at this point, exploitability on iOS depends entirely on one question, which is, can we make the kernel send a malicious exception message? Now, the answer isn't obvious, but I basically did some digging onto the deep and dark corners of X and U, and I found that there's a function called task set special port, which can be used to set a custom send write for the kernel to use instead of the true task port in certain situations, including, as it turns out, when the kernel generates an exception message. And conveniently, there's a parallel API thread set special port that does the same thing for threads. So at this point, we're basically in business. It's actually not too difficult for us to trigger this bug on iOS. So first, we're going to look up the target service port that we want to free inside of launchd. Then we register launchd to be our exception handler for xcrash exceptions. And then we call these two functions that we discovered to spoof our kernel, our task and thread port in the exception message. And then once we've spoofed our thread and task ports, we just call abort. And this is going to cause the kernel to send an xcrash exception message, which from the first call gets delivered to launchd, and from the second call contains the spoofed ports instead of the real ports. Now, all this is great, but it does beg the question. We're calling abort, which is going to like crash our process. And we definitely need to run more code if we're going to take advantage of the dangling port that we've just created inside of launchd. And if we try to use the traditional approach of calling fork or POSIX-spawn to create a subprocess, this is actually going to be blocked by the sandbox profile on iOS. So we can't use these like traditional APIs that we're aware of. Now, for a proof of concept exploit, you can actually get around this by using something called app extensions, which if you ever looked inside of your like, Finder, or sorry, Safari like share window, how it has like some other app icons in there, that's basically this feature called app extensions, which allows another binary to be part of your application that runs in separate processes. So we're just going to abuse this feature to allow us to spawn a subprocess, which is going to crash, and that's going to allow our main application to continue running the exploit after our subprocess crashes. So how are we doing on iOS so far? Even though it's more complicated, we now know how to trigger the bug, and this is going to be done by actually crashing maliciously. And we can use an app extension to free Mach ports in launchd, which is going to allow our main executable payload to continue running to take advantage of the dangling port. And additionally, our service impersonation strategy from macOS actually still works perfectly on iOS. So we can just transplant like all the code from macOS that did service impersonation works directly on top of our new exploitation technique. So all that's really left is to figure out how to use service impersonation on iOS to elevate privileges. So let's look at a first attempt at how to use service impersonation to elevate privileges. So once again, we're going to need to choose the right service to impersonate to elevate privileges. And unfortunately, on iOS, this is actually a lot more difficult because there are no unsandboxed root processes that send their task ports to a Mach service. So using the direct service impersonation get a task port strategy actually doesn't work for us. Nonetheless, even though the traditional approach doesn't work, we actually can devise our own strategy for gaining a task port using everything that we already know so far. See, exception messages contain task ports, and ReportCrash itself is unsandboxed and runs as root. So why not impersonate SafetyNet and then trigger a crash in ReportCrash? See, ReportCrash sets SafetyNet as its exception handler on launch. So if we can impersonate SafetyNet first, before ReportCrash actually starts up, then launchd is going to tell ReportCrash that we are SafetyNet, and so ReportCrash is going to set us as its exception handler instead. And at this point, we can now force ReportCrash to generate an exception For example, by sending a malformed Mach message that causes an out-of-bounds read, which is really easy. They have not checked any of this code for out-of-bounds read issues. Then basically the kernel is just going to send us ReportCrash's task port and an exception message, because we're the registered exception handlers for ReportCrash. And at this point, we just use ReportCrash's task port to execute arbitrary code. Now, this sounds great, but it actually isn't quite that easy. And the problem is that ReportCrash sets SafetyNet as its exception handler for Xcrash, which is not a recoverable exception type. By the time we get ReportCrash's task port, ReportCrash is already in process exit and is no longer going to be scheduled on the CPU. Thus, there's no way to use ReportCrash's task port to execute code. Even though we get the task port, we can't actually do anything useful with it. Nonetheless, even though we can't use ReportCrash's task port to execute code, one thing we still can do with it is to steal Mach ports from ReportCrash. And if we go back to the list of ReportCrash's Mach ports from earlier, there's one that really stands out as being very useful for exploitation, which is this thing called the host-priv port. Now, the host-priv port is another special Mach port, which is owned by the kernel. And you need to have this port in order to call many important system calls. So, for example, the way that ReportCrash registers to receive exceptions in all processes on the system is with a call to host set exception ports. And the host-priv port must be the first argument. So even though we can't execute code, we can use ReportCrash's task port to steal the host-priv port, which is going to give us access to new and exciting system calls like host set exception ports. And actually, if you think about it, host set exception ports also gives us a new way forward, which is to set a new recoverable host level exception handler and then run our same old exploit that we just did a second time. So the exploit's going to start off the same as before. We're going to impersonate SafetyNet, trigger a crash, and trigger a crash and ReportCrash. Then we're going to receive an exception message containing ReportCrash's task port, which we then use to extract the host-priv port. Once we have the host-priv port, we can call host set exception ports to register ourselves as the new host-level exception handler, but this time for a recoverable exception type like XBAD access. And then we just do the same exploit a second time. We trigger a bad memory access and ReportCrash and receive another exception message with ReportCrash's task port. And this time, because the exception is recoverable, we can just fix up the ReportCrash so that it's no longer crashing and then execute arbitrary code. So once again, this almost works, but it's not quite that easy. And actually, if you do this exploit, extracting the host-priv port does work. So we do end up with the host-priv port. But if we try to call host set exception ports, that part actually fails. And the reason for that is host set exception ports is forbidden inside the sandbox. So it's a great idea, but we also need a sandbox escape. So how are we going to go forward? We'll just escape the sandbox. It's easy. So how are we going to escape the sandbox? Well, we already have this Mach service impersonation primitive. So rather than trying to find a whole nother vulnerability, let's just reuse the vulnerability that we already have a second time. So once again, we're going to need to find the right service to impersonate. And this time, we can actually use the Mach portal strategy, which is to impersonate a service to which an unsandboxed client sends its task port. Now, this didn't work for us last time because we needed to target an unsandboxed root client, and those don't exist. However, just unsandboxed clients do exist, because this time we don't need the client to be root, we just need it to be unsandboxed, because we just need the sandbox escape part. So basically, I used a very nice technique of just impersonating every single Mach service on the phone, and eventually found through this brute force search that the Druid daemon, which is responsible for handling like drag and drop, like when you drag things on your iPhone screen, actually sends its task port to a service called com.apple.ca render server. And the Druid process is actually unsandboxed. So we do have a complete sandbox escape, which is to impersonate CA render server and then just trigger Druid to start. And when Druid starts up, it's going to send its task port to CA render server, which we're impersonating. So we get Druid's task port, which means we now have arbitrary code execution inside of Druid, which is unsandboxed. Unfortunately, Once again, it's not actually that easy. And the reason is that Apple has added mitigation. So if you actually look through the source code of XNU, you'll find that there's a new mitigation in a function called task conversion eval with a comment that says on embedded platforms, only a platform binary can resolve the task port of another platform binary. What this means concretely is that on iOS, we can't use the task port of an Apple-signed process to modify it unless our own process is also directly signed by Apple. And clearly, Apple's never going to directly sign our exploit code. So even though we have Druid's task port, we can't actually use that task port to modify Druid. So if we go back to the diagram that I poked fun of earlier, Apple's effectively blocked us at this step. So we can't use the task port that we've obtained to call Mach VM read or Mach VM write, so we can't modify Druid's memory. Now, this seems like a really robust mitigation, but I was way too far down the rabbit hole at this point to give up here. So I started looking for a way to bypass it. And it turns out there's actually a pretty big loophole, which is this function task threads. So task threads returns a list of threads in a particular task. But its semantics are really, really important. See, task threads takes an inspection right to a task. And inspection rights are not subject to the task conversion eval mitigation. Meanwhile, task threads returns a list of control rights for a task's threads. And control rights are also not restricted by the mitigation. There's no restriction on a non-platform binary controlling the threads of a platform binary, just its task port. So while it's nominally true that we can't modify Druid directly using its task port, we can call task threads to get a thread port and then control that thread's register values directly. So if we go back to our diagram from earlier, all we have to do is to ignore the mitigated path altogether and instead call task threads, which is not protected. And this is going to give us a thread port for one of Druid's threads. And once we have a thread port, we can call thread set state, which is again not protected. And then we have PC control. So we, at this point, now do have a complete sandbox escape. So first, we're going to use the launchd vulnerability to impersonate CI render server. Then we trigger the Druid daemon to start. Druid will send us its task port in a mock message intended for CI render server. And finally, we use Druid's task port along with the task thread's loophole to execute arbitrary code outside the sandbox. And so finally, it's time for the complete iOS exploit. So first, we're going to impersonate SafetyNet, crash ReportCrash, and get the host-priv port. Next, we impersonate CA render server, force Druid to start, and get Druid's task port. Then we combine the host-priv port with unsandboxed code execution inside of Druid to register ourselves as the new host-level exception handler for X bad access. Then we trigger a bad memory access inside of ReportCrash, causing us to receive ReportCrash's task port a second time. And then finally, we can now use this task port to execute arbitrary code. So graphically, I think it's a lot clearer. Here are all the processes involved, a little more complicated than the macOS case. Blanket is our attacking process on the bottom, that's in blue. Launchd is in the center. All the arrows, once again, represent having Mach send rights to the destination. ReportCrash is on the left with SafetyNet as this registered exception handler. And Druid is on the right talking with CI render server. So first, we're going to start our Crasher app extension, which is going to register launchd as its exception handler for Xcrash, and then it's going to crash maliciously, and this is going to cause launchd's send right to SafetyNet to be freed. We now register a bunch of dummy mock services with launchd until one of the service ports reuses the SafetyNet port name, at which point launchd now thinks that we are SafetyNet. Now we send a message to ReportCrash, which causes it to crash. And when ReportCrash starts up again, it's going to ask launchd, hey, who is SafetyNet? And launchd is going to reply that we are SafetyNet. So ReportCrash is going to register us as this exception handler. We now send another message to ReportCrash, causing it to crash. And this time, we are the registered exception handler. And so we get the exception message. And that allows us to use ReportCrash's task port to extract the host-priv port. And we're just going to save the host-priv port for later. Now we're going to repeat the same attack against CA render server and Druid. We start up our crasher app extension again, which registers LaunchD to the exception handler and then crashes maliciously, causing LaunchD to free its send right to CA render server. We now register a bunch of dummy Mach services with LaunchD and get the CA render server port name reused by a port that we own, at which point LaunchD now thinks that we are CA render server. We now send a message to Druid, causing it to crash, and when Druid starts up again, it's going to ask LaunchD, hey, who is CA render server? And LaunchD will reply that we are CA render server. So Druid will start talking to us and will send us its task port. We now take the task port and use the task threads loophole from earlier to get arbitrary code execution inside of Druid. And then we send the host-priv port over to Druid, and combining host-priv with unsandboxed code execution, we can now set ourselves as the new host-level exception handler for XBAT access. At this point, we now repeat the first leg of the attack. We make ReportCrash start up again and send it a message causing it to crash. And this time there is a registered exception handler for XBAT access, which means that we receive the exception message and we get a copy of ReportCrash's task port. And this time the exception is recoverable, so we use the task port to fix up ReportCrash, and then we use it to take control over ReportCrash, and we can restore the host exception handler to default. Now at this point, we can use ReportCrash's task for PID privileges to take control over LaunchD, and once we have control over LaunchD, we can fix up the damage that we did to LaunchD by restoring the ports that we messed up earlier, and then finally, we can make ReportCrash spawn our payload binary with full arbitrary privileges. And that's how you root an iPhone by crashing. So I was going to do an iOS demo, but I think we don't have that much time for it.
We can do it if you want.
Okay. It's not actually that exciting. You just get a shell. I mean, like, everyone's seen a shell. How about this? I'm going to do the setup now, and then we can do it at the very end, so we can get the more important content first. So what are the takeaways from this whole research project? First, I want to go over what we've actually achieved, and since this is a macOS conference, I'm going to focus on the macOS side of it. So we've used a vulnerability in LaunchD to take control of the sysdiagnose process, which has the task for PID allow entitlement. And as we've seen, we can now use this entitlement to take control over any process on the system. Now this is a complete SIP bypass because you have SIP entitled processes on the system, which means you can inject into them and then, where is SIP now? So you can inject into processes like TextD, which means that you also have arbitrary code execution in the kernel, which is kind of fun. We've basically managed to hop directly from an unprivileged user all the way to the kernel with one bug in a user space process. No need to bypass kernel ASLR or anything like that. So it's pretty fun. Also, the reason that I started looking at crash reporting to begin with was because it was an unconventional attack surface. Traditional attack surfaces that have been used in past exploits have been significantly hardened, which makes unconventional attack surfaces much more attractive to exploit developers. And many areas of the operating system really haven't received the security auditing that they deserve, given the huge level of privilege that they will grant you if you can successfully exploit them. So before I wrap up, there's actually one more thing that I want to talk about. A few years ago, some random guy on the internet named Patrick tweeted that he was rather fond of a particular entitlement, this thing called com.apple.rootless.install.heritable. Now, I haven't really seen anyone else extolling the virtues of this entitlement, so I figured I'd give you a quick demo of how nifty this thing can be. So just like the non-heritable version, the rootless.install.heritable entitlement allows a process to modify SIP-protected files. However, this entitlement is inherited by any child processes that start up. And so this gave me an idea, which is why not use task for PID to spawn a bash shell from inside a process with this entitlement. Bash will inherit the rootless entitlement, and so will all the processes that run inside this shell. And then we effectively get a rootless, well, I guess it's more of like a rootful shell because you unrootless, anyway. You basically get a shell where all of your SIP file system protections are now disabled because all the processes running inside this context have this rootless.install.heritable entitlement. And you do all of this without any kernel modification whatsoever, which is like kind of nice. So let's do a demo of this one. Here I am. So same thing as before. We're going to launchd port rep rootless. So actually, before I do that, let's do csr util status to show that SIP is enabled. Sudo su. So if we try to like touch system exploit, we can't do it, as you'd expect. Then launchd port rep rootless.shell. So we exploit the vulnerability, and we get a root shell, hopefully. Come on. Sometimes it takes a while. There we go, okay. So now we have a root shell, and you can see csr util status again. We still have SIP enabled, but now there's no problem at all touching system exploit. Yeah, what rootless? So you can see our exploit file is there, and we can also now exit the shell and sudo again, and if we try to remove it, nope, can't do it, sorry. So basically we have a bash shell running with this entitlement. All the subprocesses now have this rootless entitlement as well, so it's basically like, you know, classic Mac with no rootless at all in your shell, which is kind of nice. I mean, clearly you can do anything you want because you already have kernel anyway, but it's just convenient and kind of a neat trick. So yeah, let me get back. Where's my mouse? There we are. Yeah, and that's it. So thank you very much. You can find the exploit code. So the exploit code's on my GitHub. You can look at it if you want. And yeah, thank you very much. So any questions?
Was this eligible for Apple's iOS bug bounty program?
I'm not sure if I can comment on that. I'm not totally sure what the rules are about that, but yeah.
Congrats on the new job, too.
Thank you, thank you.
Super exciting.
Any other questions? Yeah.
I assume it's been patched.
Yes, yeah. This was patched in July, I believe, so it's been a while. The actual process was intermingled. So the question was, how long did it take to actually figure all of this out? The process was intermingled with a bunch of other security research, so it's not an easy answer because it's hard to kind of extract when I was working on this versus other stuff. The core of the exploit on iOS, the like strict time bounds are from between January and April. So sometime up to 4 months. The macOS part of it took almost no time at all because it was literally just like copying Ian Beer's old code and like rerunning it with a different bug. All right, any other questions? Cool, thank you very much.